Mid-afternoon session. I hope you all had a good time with the poster session. But anyway, our first talk is by Remco van Hofstad on random graph asymptotics on high-dimensional tori.
Thank you very much, and thanks very much to the organizers for the opportunity to speak here. This has so far been a great workshop, and I hope I can live up to the expectations. Talking about expectations, for those of you who have actually read the abstract and are looking forward to learning about how stochastic geometry can be used to analyze some key phenomena that arise in the context of medium access and routing wireless ad hoc networks, I'm afraid I have to disappoint you. You'll have to wait another day. I do advise you. Switch on the microphone. I should advise you to go to Bartek's talk tomorrow. Okay. Now, rightfully, my abstract is actually listed under his talk. So I was already joking that we could actually interchange the talks, but he was reluctant to do so, and I can understand why. Right. So I will be talking about percolation, in particular percolation in high dimensions. And we've already seen a few talks about percolation. This morning there was the beautiful talk of Yuval, which actually ties in rather well to my talk. So he's already been flashing some of the transparencies and the results on the transparencies that I will actually also show. So it might actually be helpful seeing it once more. And also my talk ties in very well with the talk of Massimo Francischetti yesterday. And I'll actually try to make that connection clear. Right. So often we do percolation on an infinite graph, and then we're interested in studying the phase transition. However, in real life, graphs are never infinite. So percolation was devised as a model for studying a finite object. In particular, it was used to model a gas mask. And therefore, one is interested in what happens if you actually do percolation, in particular critical percolation, on finite pieces of material. So this is one of the inspirations of my talk, and what I'll do is I'll investigate percolation on a torus. So it's a finite object in which you have vertices and bonds. And the vertices are denoted by 0 up to r minus 1. And we take the dth power of that, so we have a d-dimensional torus. And the connections go through the boundary from one side to the other side, so it's actually completely translation invariant. And then we have a certain bond set, which is here denoted by B, and this bond set can in principle be rather general. And I'll say a little bit more about what sort of bond sets we can take later on. And what we'll do is every bond that is there can either be kept or removed. It's kept with a fixed probability p, and it's removed with probability 1 minus p, all completely independently of each other. And what is the aim to study is what the structure is of the random subgraph that is left after this erasure procedure has taken place. Now, key examples here for high-dimensional tori are the nearest neighbor model, in which every vertex has 2D nearest neighbors. But we'll also be interested, and I'll explain why later on, in what is sometimes called spread out percolation, in which there are more bonds neighboring every point. So if you look at all the bonds that are connecting X, they go from X to Y to every point which is in distance, this should be X minus Y, within distance L of that point X. So this means that there are way more connections that can be made, and technically this is very convenient. Also, this is a way of spreading out connections, and yesterday we've heard Massimo talk about this, and I've jotted down one phrase that I particularly liked. He wrote somewhere that in real networks, spread out connections can be exploited to achieve connectivity at a strictly lower density value. So indeed, by spreading out connections, you can have percolation, meaning high connectivity, at a lower density of connections, which, if you're thinking about these edges as costing some money, could actually be worthwhile. Okay, and my goal is to study the structure of the largest critical cluster as the number of vertices grows large. Of course, for that we need to know what the critical value is. So that brings us to the phase transition. we've already heard some mentioning of phase transitions in percolation, and the phase transition basically says that if you take a P which is larger than the critical value, then the probability of having an infinite connected component located at any vertex in your lattice, so here we're talking about an infinite lattice, is strictly positive. By ergodicity arguments, this also means that there is an infinite component somewhere, and in fact, in these translation and in these ZD settings, this will always be unique. So for P smaller than PC, there's no infinite component. For P larger than PC, there's a unique one. Now the question, of course, is what happens at PC? Now we've been talking about holy grails throughout this conference. If I may mention one, prove that in general dimension there is no percolation at the critical point. I'm not sure whether I'll live to see the solution of this problem, because this is a very hard one. Now there have been some solutions, and Bela was already pointing towards it to some extent. In 2 dimensions, it's rather generally known that there's no percolation at the critical point. So there's no infinite component at the critical value. In 3 dimensions, we actually know nothing, period. In high dimensions, we also know something, and I'll say a bit more about that later on. Now, of course, in many of these models, in statistical physics, the area in which I tend to work, there's not just one way of characterizing what the critical value is. I mean, there's the definition of the critical value as the point where percolation starts. You could also look at a smaller piece and look at what the value is for which the expected cluster size blows up. Now, intrinsically, it is possible that these two values are different, but in fact they're not. And this is a deep and beautiful result proved around the same time by Eisenman and Barsky and Menshikov. So there really is a unique phase transition, a unique critical point, and this is the point we would actually like to investigate. So now the question is, what is the structure of large critical clusters, both in the infinite setting as well as in the finite setting? You would believe that if you perform critical percolation, so percolation with this value of P, on a large torus, that somehow the fact that your infinite model is critical is being reflected in the cluster structure of what you see on the torus. To what extent is that indeed true? Right, so a few pictures of percolation. So you just take the 2-dimensional lattice, that always works best for pictures, and what you do is you color each of the edges with a certain probability. On the left it's 0.45, on the right it's 0.55, and Bela has already explained to us why I've picked these values that way, because 1/2 is in the middle. And even when you draw the edges, you actually are not going to be seeing very much, or at least I typically don't. But when you color the clusters, actually you do see something happening. So for P smaller than PC, 0.45 on the left-hand side, the largest connected component is indicated by red, and it's large, but it's not really large. I mean, in particular, it doesn't go from top to bottom. On the right, it does, and in fact, it not only goes from top to bottom, but also from left to right. So the largest connected component really is a lot bigger. Now, as the system size tends to infinity, the probability of seeing a top to bottom crossing below the critical point will converge to 0 very rapidly. Whereas the probability of seeing a top to bottom crossing in the supercritical regime will converge to 1 very rapidly. So there really is a big distinction between the two different phases. Okay. Now, the question is, what happens at the critical point? Well, there the situation is not so clear. So I've done the same thing. I've made the square a bit bigger, and I'm coloring the 3 largest connected components. This is one realization. Okay, well, that's what it looks like. But if you do a different realization, it all of a sudden looks rather different. In particular, the size. And if you do another one, all of a sudden it looks like a supercritical thing that is happening. So what you see is large fluctuations at the critical point in terms of the size of the largest connected component. That's something that you will not see in the subcritical regime nor in the supercritical regime, where the largest connected component tends to be highly concentrated. So if you do 20 realizations, you will not see a lot of fluctuation in the particular size. The leading order asymptotics will be the same. At the critical point, that's different. So this is a picture for 2 dimensions, but the same ought to be true in any dimension. And I'm in particular interested in high dimensions. So why am I interested in high dimensions? Well, one of the reasons is we can actually do something there. That might actually be a good reason. But also, there's a certain feature of high-dimensional percolation that makes it easier to understand. Somehow the geometry of percolation trivializes in a certain sense. So the physics prediction is that percolation in high dimensions is very much like percolation on a tree, at least when you're not interested in spatial aspects. So in particular, at the critical point, there should not be an infinite component, because critical branching processes die out. And also, something that is often used in physics in order to describe critical behavior, namely critical exponents, and I'll give more precise definitions on the next few transparencies, the critical exponents ought to be the same as the ones on the tree. Now, percolation on a tree is a branching process, so for that we can basically compute everything. So the survival probability on a tree is the branching process survival probability. The percolation probability on a tree is the same as the branching process survival probability. The expected cluster size is the same as the expected total progeny in your branching process. And all of these things you tend to be able to compute on a tree, not on ZD. Yes?
Why 6? I'm sure you got this question before.
Yeah. I can say something about that. But let me postpone that for a little. Yeah. In fact, it's not always 6. So if that answers your question to some extent, then. But there's something happening at 6 that is special, and I can say something about that after the next transparency. So what is the informal reason? Well, in high dimensions, somehow the geometry plays a less important role. So that's sometimes phrased as the geometry trivializes. Somehow what that means is that if you have a path, it goes from one point to the other point, even when the path is not very long, you're sort of already infinitely far away. So whatever you see close to the one point is going to be almost independent from what you see close to the other point. Now, if it were to be perfectly independent, you would have a tree. Right? It's not going to be independent. For example, the critical value of percolation on ZD is not going to be 1 over 2D or 1 over 2D minus 1. It's something much more complicated. But still, it could be that the critical behavior is related. And that's what I'll be talking about today. So, in particular, what this says is that if you look at faraway pieces of clusters, connected components, they should be close to being independent. And we all know that if things are completely independent, then we can basically understand everything. But for example, if you look at convergence towards Brownian motion, it's not precisely necessary that the subsequent steps are completely independent. Some weak dependence is also fine. As long as the weak dependence is rather local, if it's not too bad, you're still going to get Brownian motion as a limit. So, the same thing applies here. Clusters, pieces of clusters that are not too far away, they're not going to be independent. But if they're close to being independent, you might still see the same scaling limit. So that's what we're after. And then, of course, the question as to why it's 6, that's quite relevant. Okay, so a partial answer comes here. So, critical exponents, I've already been mentioning them. Critical exponents are the powers in power law relationships that you might find in your model. For example, if you look at the critical value, then we know that if there's no percolation at the critical value, that the probability that the cluster is infinite is actually 0. So therefore, the probability that the cluster is greater than or equal to n should decay to 0 as n tends to infinity. Now in physics, it's rather common to immediately assume that if something converges to 0, that actually it converges to 0 as a power. Okay? So indeed, in high dimensions it does, and it actually decays to 0 like 1 over the square root of n. Note that that is precisely what happens for critical branching processes. The probability that the total progeny, or the total number of individuals in a critical branching process, is at least n at the critical point decays like 1 over the square root of n. Okay? So we see a critical exponent that appears here, which we can interpret in terms of the problem for branching processes. Okay? So in particular, this implies that the percolation function is continuous. Because this tends to 0, there's actually not going to be percolation at the critical point. Now we see that reflected here again, namely if we look at the percolation function, so the probability that the connected component of the origin is infinite at a value p which is larger than pc, and this is going to be strictly positive because we're supercritical, but it will converge to 0 as p approaches pc. And the way how it does that is approximately linear in the distinction between p and pc. That's also something which is true for branching processes. If you look at the survival probability of a branching process with mean mu, and mu is larger than 1, then if you have a finite variance branching process, the survival probability will be proportional to the distinction of the mean with the critical value 1. And it's something similar that you see appearing here. On the other hand, if you look at the expected cluster size, now p has to be smaller than pc, otherwise it's going to be plainly infinite, then that blows up at the critical point. So in particular, the expected cluster is infinite at pc. And the way how it does so is like 1 over the difference between pc and p. So these values that are written here it's 1, here it's minus 1, therefore also 1, here it's 1 over 2. These are called the critical exponents. So this says that the critical exponent beta, which is associated to the percolation probability, takes on the value 1. This says that the critical exponent gamma, which is the negative of this exponent, also takes on the value 1. This says that the exponent delta, so this exponent is often written like n to the power minus 1 over delta, for some reason. Delta is equal to 2. And there's a final here that says that the probability that 0 is connected to a very far away point, x, as x tends to infinity, is proportional to 1 over x to the power d minus 2. And often this exponent is written like minus d minus 2 plus eta, or minus eta, and then we see that the value eta is actually equal to 0. Right, so I still have to explain the d is equal to 6 business. Okay, well, let me say a few words about the proofs. I'm actually not going to go into the proofs because all of these results are for percolation on the infinite lattice, and that's not going to be the subject of my talk today. The subject of my talk is going to be percolation on a finite torus. But still, it's actually quite useful to understand what happens on the full lattice. Right, so what do these proofs use? Well, and basically, there are 2 steps here. So there's a couple of papers that somehow do these 2 steps, and you really have to combine the results from the different papers in order to get all of these claims. So the idea was, by Eisenman and Newman, and also by Barsky and Eisenman, that you define a geometric condition for percolation. It's called the triangle condition. And I can write down what it is, despite the fact that it might not tell you much. So you basically do this. Here's 0, here's x, here's y, and you sum over x and y. Now I've drawn lines, but it may not be obvious to you what these lines mean. But what these mean are independent connections from 0 to x, multiplied by the probability that x and y are connected, multiplied by the probability that y and 0 are connected. So you get the sum over x and y, probability at pc that 0 is connected to x, probability pc that x is connected to y, pc, y is connected to 0. So this is called the triangle diagram. And when this triangle diagram is finite, then you get that beta is 1, gamma is 1, and delta is 2. Okay. Now, of course, that does not immediately make a relation to the dimension. However, when you also believe that this is true, and in fact, if you look carefully on the right-hand side here, you may recognize the Green's function of Brownian motion. So this is very closely related to the expected number of hits to x of a random walk started at 0. Of course, we're in high dimensions, so this is transient. This decays like 1 over x to the power d minus 2. So if you substitute that in, you actually get that that sum is finite if and only if d is greater than 6. So you cannot expect this behavior together with this triangle being finite for d less than or equal to 6. So that at least suggests that you need to have different critical exponents. And in fact, that argument can be made rigorous, saying that it's impossible to have these or some other critical exponents while the dimension is smaller than 6. So this makes a very clear relation between dimension and mean field critical exponent. And it really does suggest that d greater than 6 is really the right thing. And I believe that when d is 5, you really get different critical exponents, despite the fact that I have no idea what they should be. Okay? So this is one part of the proof. Now, of course, this is very important because it gives an explicit condition as to when the critical exponents take on their mean field values. But it's not everything, right? Because you start with a condition that we actually do not know how to prove. And under that condition, which may actually be equally hard as actually proving that beta is 1 or gamma is 1 or delta is 2 in the first place, under that condition we actually get that these critical exponents exist. So we need a second part of the argument, and that's where the Lace expansion comes into play. We need a second argument that investigates this 2-point function and actually proves a result like that or a similar result in k-space, or the Fourier transform of this function. So that's what the Lace expansion does. And if you put these two together, you get that these critical values come out. You actually get a lot more. Okay, so I've been dropping here this name Lace expansion, and many of you will not know what that is. I'm not sure whether half an hour would be sufficient in order for me to explain what it is, and I'm not going to take that half hour. But somehow, very high up in the sky, what it is it is a perturbative method that allows you to compare the 2-point function for critical percolation to a Green's function for branching random walk, or for a normal random walk. So basically what it does is it says, if 0 is connected to x, then there must be a path of occupied bonds connecting 0 to x. That path is not going to be unique. That's somehow going to be very close to unique. So you can think of it as being a random walk path. You have to make that precise, and the way how you make that precise is by doing analysis. So there's a lot of analysis involved in performing a Lace expansion proof. And it's actually in this analysis, I mean, I'm writing here that it's a perturbative method, and perturbations are often nicer when you have a small parameter. So that's why this model, this spread out model, is actually nicer, because it produces a small parameter. So here the small parameter will be 1 over L to the power d, and the results will be true for d greater than 6. Now you can also do it for nearest neighbor percolation, as it is also written in the theorem. But then you need d sufficiently large. Again, it's a perturbative method, and the role of the small parameter is now being played by 1 over 2d. Well, 1 over 2 times 6 may not be small enough, right? So if you want a small parameter, you may actually have to take d to be much larger. Universality, which is one of the big claims of the physicists, will immediately tell you that these results also ought to be true for d greater than 6 and the nearest neighbor model. That's something we don't know. That's another quite cool problem to look at, but it may not be such an easy one. Okay, so what does all of this tell us? Well, it tells us that clusters are alike branching processes. Of course, clusters also have geometry. So I think a better way of saying that is that clusters are like branching random walk. Critical percolation clusters are a lot like critical branching random walks. So that's somehow the mean field model, and any critical exponent that you can compute for critical branching or critical branching random walk, that critical exponent is probably going to be the same as the one that you will get for high-dimensional percolation. Okay? So it gives a suggestion as to what the mean field model should be. However, recall that we were not initially interested in percolation on ZD. We were rather interested in percolation on a torus. Now, a torus is a finite object. So this finiteness somehow must enter the picture at some point in the game. Now, if we try to stretch this heuristic that I'm trying to convey here, if we try to stretch that a little bit further, one thing we could say is that the geometry plays no role. The geometry becomes trivial. Now, if the geometry plays no role, then percolation on the torus should be very much like percolation on the complete graph of the same size. That's the Erdős-Rényi random graph. And we've heard Yuval speak about this morning. I'm going to recap some of the ingredients. For percolation on the complete graph, or the Erdős-Rényi random graph, we know a lot. We know a lot about the phase transition. So, what does that mean? Well, it means that if you take P to be 1 plus epsilon divided by the total number of vertices, which I call V in order not to confuse people with notation that will come later on. So V stands for the volume, that's the same as the number of vertices. If epsilon is positive, then you get a largest connected component which has size the number of vertices. In fact, it's highly concentrated, etc., etc. If epsilon is negative, on the other hand, so in between -1 and 1, then the largest connected component has size log V. And you can study what happens for epsilon being equal to 0, and then you get non-trivial scaling behavior. So volume to the power 2/3. In fact, that is true throughout what is called the critical window, which is of the form 1 over V times 1 plus something of the order volume to the power -1/3. Okay? Now, why is it reasonable to have a critical window? Well, if you think about an infinite graph, in infinite graphs, phase transitions tend to be sharply located on a specific point. You can't really expect that to happen in a finite graph, because everything is continuous. All my functions that I'm writing down are going to be differentiable, and they have all properties which you like. So the best thing that can happen is that you have a steep increase of some sort. Right? But if you have a steep increase of some sort, then it means that there is a certain regime in which the order of magnitude of the largest connected component will be the same as what happens when you take the parameter to be equal to 0 precisely. So the phase transition is being smeared out. It's not a critical value, but it becomes a critical window. That's what happens. And this identifies precisely what the critical window is. And Yuval's talk this morning has shown what happens if you take this lambda to be large. So if this lambda still depends on the dimension, on the volume, and actually tends to infinity. And we see that the largest connected component has size 2 times epsilon times V, and is highly concentrated. And Yuval has drawn this beautiful picture as to what the structure of this largest connected component looks like. The second largest component will be much smaller. So at the critical point, the largest connected component has size volume to the power 2/3, actually multiplied by a random variable. So if you look at all the ordered clusters and multiply them by volume to the power -2/3, then this sequence will converge to a sequence of non-trivial random variables. That's a result by Aldous. But in a certain sense, it's building on earlier work. So he calls it a folklore theorem in his paper. But I do think that he's the first one to actually identify what the scaling limit is, so what the random variables are. There are many extensions. For example, Yuval has spoken this morning about what the diameter is like. So it's of the order volume to the power 1/3. And there's a recent work by Luigi Dario-Berri, Nicolas Broutin, and Christina Goldschmidt, which actually studies what the scaling limit of the clusters are. So these clusters can be trees, but they don't have to be. They could have cycles. But the cycle structure will be relatively sparse. There will be few cycles. And it turns out that you can actually prove that these graphs, as a metric space, converge weakly to some limiting object. And they've identified the limiting object. So now the question is, whether anything like that is also true for percolation on a high-dimensional torus. So on a high-dimensional torus is the largest connected component of the same order as the one on the Erdős-Rényi random graph. Okay. So first of all, what is the largest connected component? Well, we look at the clusters of vertices on the torus. I give a subscript T to denote the torus, because later on we'll actually be dealing with clusters both on the torus and on ZD simultaneously. You look at the number of vertices in there, that's what these bars indicate, and then you take the maximum overall vertices. So this really is the component that contains the most number of vertices. And in my statement, V will always denote the volume of the graph, and on a torus that's R to the power D, the width to the power D. And then, in the same setting as in the previous theorem, so D much larger than 6 and nearest neighbor bonds, or for D greater than 6 and sufficiently spread out bonds, it is indeed true that Cmax is of the order volume to the power 2/3. If you write it down precisely, then what it says is that Cmax is with high probability smaller than a large constant times volume to the power 2/3, and with high probability larger than a small constant times volume to the power 2/3. Now this probability probably converges, which is something we actually do not know, but if this converges, it will probably not converge to 1. So this will only be close to 1 if this large number actually becomes quite big. Now another thing we can prove is that this Cmax multiplied by volume to the power minus 2/3, which is tight, that's what this result says, and also 1 over this random variable will be tight, we can show that it's not concentrated. So that reflects these pictures, which are in the 2-dimensional case, where you really see that the red set in size varies quite dramatically if you go from one realization to another. And that's precisely what you would believe to be true only at the critical point.
So B is quite interesting, right? Because W equal to 1 is kind of interesting. So how true is that statement for W close to 1?
Well, it's still true, but B will probably be much larger than 1.
Yeah, but still, I mean, so that's a
Well, then it says that the probability is greater than or equal to something negative.
I see.
If omega is 1, it's just 1 minus B,
So,
and
okay,
B is
so-
gigantic, then it's a useless statement. So you actually only get something out of it when you make omega to be much larger than B. And we don't really have any good control over B, unfortunately. Yeah.
So
Good
your
question.
statement essential that for all sufficiently large omega result, because for small omega result is trivial.
Yes? But it doesn't hurt to write down a trivial statement. It removes one condition from the theorem, which I always like.
Okay.
But you're absolutely right, yes. Okay, so what this says is that the cluster size for percolation on a high-dimensional torus at the critical point, at least in terms of the volume, is rather similar to the one on the Erdős-Rényi random graph. Now you may want to think about other features. For example, is the same true for the second largest component, or the third largest component, or the fourth largest component, etc.? This turns out to be true. So we get basically the same result, not just for the first one, but also the second, the third, the fifth, etc. The peculiar thing is that we can't quite show that the second one is non-concentrated. I believe this to be true, but our proof doesn't immediately give that. Also, we've seen that for the Erdős-Rényi random graph, the diameter of the largest connected component is of size volume to the power 1/3. That's also true in this case. The power of omega becomes a bit worse, but it's still true. So, at least in terms of volume of the largest connected component, and in terms of the diameter of the largest connected components, the critical clusters for percolation on high-dimensional tori are very much alike those on the Erdős-Rényi random graph. Now there's a final result on lazy random walk mixing time that also Yuval talked about for the Erdős-Rényi random graph. In fact, their result is also stated in a more general setting, which they apply to the Erdős-Rényi random graph. But the conditions for that more general setting are actually easily verified using the results that we proved in the previous theorems. So we get the same result, namely that the mixing time of any of the large connected components scales with volume. And it probably is a random variable. So if you look at this object and divide by V, it's probably again non-concentrated. Yes, that's 1 over 34. Yes, that probably is not optimal. But it's a value that works. Yeah, good question. Yeah. So I would believe that this object is non-concentrated either, but it's something that we haven't shown. Okay. So the title of my talk is Random Graphs Asymptotics for subgraphs on high-dimensional tori or something like that. So the behavior we see of the objects that we can actually study is the same as on the Erdős-Rényi random graph. So that's why we call this random graph asymptotics. Of course, we haven't quite proved all the results that have been proved so far for the Erdős-Rényi random graph, and probably not all of them are provable with this kind of methodology. We can probably go a bit further. I'm not sure. Interesting questions that are still open are whether the scaling limit is the same as the scaling limit for the Erdős-Rényi random graph. I'm not sure. This is one of these problems where you ask me on Monday, I might say one thing, on Tuesday another thing, and on Wednesday a third. Definitely, if the scaling limit is related, then there will be different constants involved. It's like with random walk always converges to Brownian motion if the mean is 0, but you know there is this parameter which is the variance that actually changes life a little bit. Here that will occur too. So there will be a parameter related to variance that will appear. But the question is, if you take that into account, will the scaling limit still be the same as on the Erdős-Rényi random graph? It's not clear, but I wouldn't be surprised. Another open problem is the behavior in the supercritical phase. Somehow the supercritical phase, P larger than PC, is somehow always more difficult than what happens in the subcritical phase. So we have very good control over things in the subcritical and in the critical regime, but the supercritical is much harder. Somehow in the supercritical regime, the geometry enters in a more profound or pronounced way. And we don't really have a good control over that. It would be interesting to understand that in a more general setting. So the work that I've been speaking about is based upon 2 papers with my former PhD student, Marcus Heidenreich. But actually they've been working, this work has been building upon earlier work with Borks, Chase, Slade, and Spencer. So Thomas Wuchak always calls these the bitches papers. There are 3 of them. I kind of like this acronym by now. I've gotten used to it. And the results do apply more generally to that setting. So you can think of other settings where you have somehow a high-dimensional torus. Well, the easiest example would be the n cube, which I often denote like that. Take 0, 1, you raise it to the power n, and you let n tend to infinity. So this is a high-dimensional torus. In a certain sense, it's on the other extreme of the spectrum compared to fixed dimension and letting the width tend to infinity. Here the width is as small as it can be, and you let the dimension tend to infinity. So this is also in very high dimension. And personally, I would believe that the behavior here at criticality, however you would define that, ought to be the same as for the Erdős-Rényi random graph. So to a certain extent, we know some of these things, and to a certain extent, we actually do not. Okay. So I started my talk by discussing that percolation never lives on an infinite lattice in reality because everything we see is actually finite. Now you may wonder what these periodic boundary conditions are actually meaning in reality. Well, in reality, the periodic boundary conditions may not be there, and you may instead look at something else with different boundary conditions. Now the question is, are these boundary conditions relevant? At criticality, often boundary conditions are relevant, and we see that recurring here. So we've seen that if you have periodic boundary conditions, so that's percolation on the torus, that's what I've been talking about so far, then the largest connected component has size volume to the power 2/3. Now suppose instead you look at bulk boundary conditions or free boundary conditions. So in free boundary conditions, you just chop off everything at the boundary. What would the largest connected component be then? Well, it should definitely be smaller, because you're not allowed to wrap around. But it becomes a lot smaller. In fact, it's bounded from above by r to the power 4. And for bulk boundary conditions, so I have to explain what that means, you take a vertex x and a vertex y in the cube, and you say that they're connected when there is a path in the infinite lattice that connects them. So you're only looking at vertices inside the cube, but the paths are allowed to go outside of the cube. Okay? That's called bulk boundary conditions. And for bulk boundary conditions, Eisenman showed that the largest connected component is of order r to the power 4. Now, r to the power 4 is much smaller than r to the power 2 times d over 3 when the dimension is greater than 6. So there's a big difference between the behavior with bulk boundary conditions or free boundary conditions when you chop everything up, or when you allow to go around the torus very often. And in fact, that is one of the features that is crucial. So if you believe that geometry plays a small role on the torus, well, there's one way how you can achieve that. If I want to connect 2 points that are very far away, if I wrap around the torus very often, then I sort of forget where I started from. And therefore, the probability of connecting these 2 points will be almost constant. That's something that we can actually control. How often you wrap around the torus in order to connect 2 points on the torus that are not too far away. If you start with 2 nearest neighbors, probably and you condition them on being connected, then probably the path will be the direct bond connecting them. Right? But if they're very far away, you actually do wrap around the torus very often. And then I mean very often. Something like volume to the power 1/6 times or something like that. Okay, so what we see here is, and this is sometimes called finite size scaling, it is that the scaling of the largest critical component is sensitive to the boundary conditions. So what about the proof? Now, there's one part of the proof that I would actually like to explain in a little bit of detail, and that is a coupling. So there's a coupling relating the cluster size of a vertex, let's say the origin, on the torus to the one on ZD, such that one is always larger than the other. It's of course a very useful and important ingredient in studying percolation on the torus, if you have a good understanding of percolation in high dimensions, which we actually do. And then there are various lace expansion results, which we actually in the proof of the main results do not make use of. There are various lace expansion results in the Beaches papers that basically investigate all sorts of critical exponents for percolation on the torus. So we rely heavily on the results, but not on the methodology. The lace expansion really is a tricky object. So these papers actually give us an excellent control over various quantities, such as expected cluster size, but also tail probabilities, cluster tails, for subcritical or critical P's. And then we combine these results together with the mean field results for percolation in high dimensions, various critical exponents, like the ones that you've seen in theorem 1, beta is 1, gamma is 1, etc. In fact, what we need is gamma is 1, the critical 2-point function eta is 0, and another critical exponent which I haven't defined, which ought to be equal to 1/2, in order to complete the result. Yes?
Just trying to understand point 1, because I thought you just told us that's useless, right? You said
Did I?
Yeah, so why is that used in some sense?
I'm saying that boundary conditions play an important role.
So in some sense,
At the
point
critical
1
point.
is useless, right? So
No, it's not. No. It might still be that boundary conditions play an important role, but the expected cluster size could still be related in a technical way. But we'll get back to that. So this is the result. You can produce a coupling of percolation on ZD and percolation on the torus in such a way that the cluster size of the cluster on the torus of a specific point, which I denote here by the origin, is almost surely bounded from above by the cluster size of the origin on ZD. Now, Okay, one remark. I've always found this very confusing. If they're ordered in any way, they have to be ordered this way, because the right-hand side can be infinite and the left-hand side cannot be. Okay, so that's a good sign. Now the question is, how does one actually prove this? Now, I'll try to make a picture that conveys the construction. I'll do this in 2 dimensions, but the same construction actually works in general dimension. And the idea is to tile the plane. So what I'll do is I'll tile the plane, and then, of course, the connected component of the origin, if I would use everything of the plane, would just be the connected component on ZD. So if I can somehow build in also the cluster of the torus in the same sort of tiling of ZD or Z2 in this case, then we might be able to prove this construction. So how do we do this? Well, I put the torus here. Here's the origin. I'm trying to compute the cluster of the origin. And now I'm going to be tiling the plane with different copies. They're all the same. And this goes infinitely long. Okay. So for percolation on ZD, this point, which is neighboring this tile, is actually different from this point. But for percolation on the torus, these are identified. So we'll have to deal with that. So what I'll do is I'll start here at the origin and start exploring the cluster. So I'll find the number of occupied bonds, and I will also find the number of vacant bonds. Maybe make the picture a bit bigger. So these are my occupied bonds, and these are my vacant ones. I explore only the connections that live inside the torus completely. So I stop and I reach the boundary. That's crucial. Okay? And it means that every bond that actually touches a vertex in the cluster that lies entirely inside the torus will actually be vacant. That's nice. Now when I don't hit the boundary, for example, like that, then there's actually not going to be any distinction between the cluster on the torus and the cluster on ZD. They're just identical. So the only distinction that can arise is when I hit the boundary. For example, like that. Okay? Now the whole point is, what I would like to do is start exploring the cluster again from this point and not from that point. Or that point, the point which is equivalent to it. Okay? Of course, I've already discovered the status of a number of bonds. So these I will be coloring red. These are all the bonds that I found, both vacant and occupied. Something like that. I've made it hard for myself. And now what I'll do is I'll explore again from this point, which is on the boundary between two of the tiles, all the connections that lie inside the next tile that neighbors it. Okay, so I might get something like that. But when I touch one of the red bonds, I'm actually not going to inspect its occupation status. Just ignore it completely. The reason for that is quite obvious. In fact, for the torus, I already know what its status is, because I just have to look here. I will know what the status of that bond is. So just ignore it completely. Then iterate. It might of course be that you again go to the boundary, either here or there, and then you iterate. Every time when you find a couple of bonds, either occupied or vacant, you color them red in all of the other copies. That ensures that you're only going to be using those bonds once. Okay. So if I do it that way, and at some point I'm done, then what I get, or at least in terms of the numbers, is precisely the connected component of the origin on the torus. So in fact, if I want to get the component back, what I need to do is map all of the found occupied edges back to the tile that I was interested in the first place, this one, and then count how many vertices I have. Of course, that's not going to matter. It's going to be the same number of vertices that are going to be connected to the origin before of wrapping it back. Okay? Now, if I want to go to ZD, what I do is I ignore all of the red bonds, make them make them unexplored again, and then see whether there are any ones, for example this one, that I haven't explored yet, and start exploring from those. When I'm done with that, what I'll get is the cluster from the origin on ZD. Because whether something was read before at some point in the game is actually irrelevant. Therefore, what you will get is the connected component on ZD. And it will clearly be bigger because there's more to be explored. And there we go. That's the entire proof. We were not the first ones to do something like this. There was an earlier argument by Benjamini and Schramm. The nice thing about this particular construction is that it also tells you something about a lower bound. So if a vertex is connected to a vertex on ZD, but it's not connected to the point corresponding to that vertex on the torus, it must mean that some bond was chosen twice and was vacant in one of the constructions and occupied in the other. So it gives you also a way of proving a lower bound on this construction, particularly on the two-point function. So this relation immediately gives that the expected cluster sizes are related. So if you then take a p which is smaller than a critical value, then you actually also know something about the expected cluster size on the torus, and that actually does help you in proving relating the bounds using also the earlier work. Okay, so how can that be used? Here's a small example. Suppose we were to look at the number of vertices inside connected components of size at least k. Okay, that's a random variable. It's a sum of indicators. And the nice thing is that it's a sum of indicators dealing with a single cluster, not with the maximum over all clusters. Also, there's a direct relation between this random variable and the largest connected component, in the sense that the event that Cmax is greater than or equal to k is the same as the event that Z greater than or equal to k has size at least k. Because if this is true, there's at least one connected component of size at least k, so this event is true. If this event is true, then for all of the k points that are in my Cmax, the indicator will give me a 1, and therefore this event will also be true. So the two events are the same. Okay? So this idea has been rather fruitful in all of the papers that I've been referring to so far. We've made use of this, this sequence of random variables. So how can we do that? Well, for example, if you want to prove that the Cmax is with small probability larger than some large constant times volume to the power 2/3, what you can do is say the probability that this occurs is equal to the probability that this Z greater than or equal to k is greater than or equal to k. Use the Markov inequality for that. And the Markov inequality, this is a sum of indicators. The probability that these indicators will be occupied is the same for every vertex, because it's a translation invariant system. Therefore, you get a volume over k times the probability that the cluster on the torus has size at least k. Okay, but we've just shown that this random variable is stochastically dominated by that random variable. Therefore, the probability that the cluster on the torus is big is actually smaller than or equal to the probability that the cluster on ZD is big. But for that we already know what the critical exponent is. Now substituting it in, what you see is that you get 1 over k to the power 3/2, and in order to cancel this v, you need to take k to be of the order volume to the power 2/3. But that was precisely what we were after in the first place. So this immediately proves the upper bound, just knowing that delta is equal to 2 for percolation on ZD. This is the whole proof. Not very hard. Okay? Now you can also do the lower bound, again looking at this Z greater than or equal to k object, but it's a little bit more tricky. In fact, it's quite a bit more tricky. So if you want to study the probability that Cmax is smaller than k, that's the same thing as saying that Z greater than or equal to k takes on the value 0, and then you can do a variance estimate to estimate that probability. then you need to start bounding these variances, etc. I will not go into that. But in fact, over lunch or breakfast at some point, Yuval suggested me to propose some problems. I always listen very attentively when Yuval suggests something. So here's a list of problems. They're ordered in levels of difficulty, in my estimate of it. I'm not sure what that is worth. In the talk by Massimo, we've already seen that spreading out connections actually decreases the value of PC, which is actually quite nice. Now, there have also been suggestions that long-range connections might be important too. So there's a particular model of long-range connections where the probability that an x, y is occupied is the norm of x minus y to a certain power, which is larger than d. And in these models, you can also investigate what the percolation probabilities are. Okay? Now, in work with Markus Heidenreich and Akira Sakai, we've managed to show that, again, the critical exponents take on the mean field values. So gamma is 1, delta is 2, beta is 1, when d is greater than 3 times the minimum of alpha and 2. It's basically the same computation as came out of that. But here, of course, we shouldn't be comparing paths in percolation clusters to Brownian motion, but rather to Levy processes, because they might actually jump very far. So also the Green's function is a bit different. And that's actually what gives rise to this problem. I would believe that if you would do something like this on the torus, you would again get largest connected components that are of the same order of magnitude as the ones you get for nearest neighbor or finite range percolation. So prove that. Prove that the largest critical cluster on the torus is again of the order volume to the power 2/3. Another thing you might do, and this is more in the direction of what Massimo was doing, is to take a real spread out model in the sense that the width over which connections take place, so all the bonds have the same probability of being connected, but the width over which the bonds take grow with n, grow with the volume. They have to grow like that. Of course, if the dimension is very low, you're allowed to use many connections. So you're much closer to a branching process. So it might be possible, in fact, in this setting, to identify the supercritical phase. That's probably more difficult than this problem, but it might still be doable. And then there are two questions that I've already stated. In general, the supercritical phase. That's a very nice problem. And the scaling limit of the largest connected components on the torus. Prove or disprove that it's the same as the scaling limit on the Erdős-Renyi-Random graph. And as I said, I don't know which of the two should be true. Thank you.
Take some questions.
You mentioned something about how connections between two faraway vertices manage to wrap around the torus.
Yep.
So you said that it wraps around v to the 1/6. Is that correct?
Yeah, something like that. Yeah.
You know, I mean, so could you
Okay.
say maybe a few more things about this?
Yes, I can. Let's do it like that. So in the Eisenman picture, you take a ball, you take a cube of radius r, and then the largest connected component has size r to the power 4. Now here it's going to be somewhat different, right? Here the largest connected component has size volume to the power 2/3. So suppose I were to unwrap the largest connected component. How often should I unwrap it before I'm actually done? Well, if you do this volume to the power 1/6 time, and it is the case that if I raise this to the power 4, I get volume to the power 2/3. That's rather suggestive. That is the right value. So we can say something about that if you take 2 points which are far away, for example, 2 uniform points along the torus, that the probability that after unwrapping they're connected within a cube of width smaller than epsilon times volume to the power 1/6, that will actually go to 0 when epsilon tends to 0. So there are partial results, but maybe not as sharp as you would like.
So can part of this be extended to continuum calculation?
That's a-
Boolean type.
My guess would be yes. By discretizing continuum percolation, doing a lace expansion for that, and well, it's going to be a lot of work. Some work has been done in that direction, but I'm not sure how much. So I would guess yes, but it's a major investment. So. But I mean, this is related to the question of what are the critical exponents in Massimo's model. So if you take your f to be similar to what this is, so something like 1 over the distance to the power of d plus alpha, and I'm guessing that you get mean field exponents. Probably when you take something which is smaller, then it's not going to be the case. So it's clearly related.
Any further questions? Well, let's thank the speaker.